Look around you. Everything is changing. Physical changes just change shape, like melting ice. But chemical changes make something. Can you spot the difference?
We look at a burning candle and usually see a steady light and a bit of warmth. It's a common object we take for granted. But if you freeze time and zoom in, that calm glow disappears. You're looking at a complex, invisible interaction of molecules colliding at thousands of degrees. Matter transforms around us constantly. Ice melts in a glass, vegetables are chopped for a meal, and water boils on the stove. We instinctively try to organize these changes into neat categories. But to understand what is actually happening to the matter, we need a way to distinguish one type of change from another. The burning candle is an ideal example because it doesn't fit into just one category. Tracking the matter within it requires looking at two fundamental paths, a change in appearance and a change in identity. Look at the base of the flame. The intense heat radiating downward hits the solid wax, causing it to melt into a liquid pool. This is a physical change. While physical properties, like state and shape, shift, the substance's actual identity remains the same. No new substance is formed. Because the molecules haven't changed, this process is reversible. When wax cools and solidifies, it returns to its starting state. You see this same principle when you crush a piece of chalk into powder. The size and shape have changed, but the material itself is still chalk. Other physical changes might be harder to undo, like folding a piece of paper or popping a balloon. Even if you can't easily get the original shape back, the paper and rubber haven't transformed into something else. In a physical change, the matter remains identical at the molecular level. Its true identity survives the transformation intact. Since the wax and cotton wick are in constant contact with oxygen, why don't they just start burning at room temperature? The wax and wick are combustible substances. They are materials that have the potential to react with oxygen to produce heat and light. But having oxygen and a combustible material is not enough. To trigger the reaction, a specific thermal barrier must be crossed. This graph represents the ignition temperature, the minimum temperature required for a substance to catch fire. Until a material reaches this exact threshold, it will not burn. You can observe this by using a magnifying glass to focus sun rays onto a piece of paper. The paper heats up in that one spot until it finally crosses that thermal line and begins to burn. Crossing the ignition temperature moves a substance beyond a simple physical change and into a process that creates something entirely new. In our candle, the pole of liquid wax is drawn up the wick and evaporates into a hot gas. When this wax vapor meets atmospheric oxygen inside the flame, the molecules collide, break apart, and instantly reform into different structures. This is a chemical change. The original wax molecules are gone, replaced by newly created substances with entirely different properties. Since these new substances are often invisible gases, scientists use specific tests to prove they exist. One method involves capturing the gas from a flame and passing it through clear lime water. If the water turns milky or cloudy, a reaction has occurred. That cloudiness is caused by the formation of calcium carbonate. It is physical evidence that carbon dioxide gas was produced during the burning process. We see these new substances form in many other reactions, like the bubbles produced when mixing vinegar and baking soda, or the white magnesium oxide powder left behind when a magnesium ribbon is burned in air. Unlike a physical change, these chemical changes result in new substances that cannot be returned to their original form. When we look at the candle again, we can see that it involves both physical and chemical changes happening at the same time. The physical changes of melting and evaporation are necessary steps that feed the chemical change of combustion. Categorizing these events helps us understand the underlying rules of the physical world. It allows us to look at any transformation and identify the specific mechanism at work. This applies to the slow chemical change of an iron nail rusting, or the physical change of a tree branch being snapped by the wind. It even explains biological events, like the chemical reaction in a firefly's tail that allows it to emit light without producing heat. Every transformation leaves a signature, revealing whether the matter merely shifted its form or became something entirely new.